So it's our pleasure today to have Leroy Chew here, who will tell us about QBF proofs and strategy extraction and other things worth knowing.
Yes.
So please take it away.
Thank you for the introduction. Yes, as I said, I'll be talking about QBFs. So in the first few slides, I'm going to be just introducing QBF. We're going to look at some examples of the QBF proof systems. Then we're going to get into some proof complexity. So in particular, in proof complexity, we like to look at lower bounds. And also on the other side, the more positive side, we look at P simulations. And within these two sections, we'll be looking particularly at this strategy extraction technique, which was the other part of my title. I think somewhere during this P simulation section, we are going to hit 50 minutes. And then some more difficult material is going to appear, which is going to include this final section where we look at some of these a bit more thorny proof systems and maybe go into detail about a trade-off between having strategy extraction and maybe not having strategy extraction for some additional power. Okay, so first, let's motivate QBFs. And we motivate QBFs by looking at the polynomial hierarchy from complexity theory. So at the bottom of this hierarchy, we have P, polynomial time, and at the top we have P space, that's polynomial space. And we have this various ladder of various different complexity classes that starts at NP and looks at various alternations to give you this polynomial hierarchy, which is denoted here as PH, which is the union over all these classes, and P space sits above that. So problems such as SAT and topology are on the first level of the hierarchy. And when you might start moving to the second level of the hierarchy, you get some sort of like non-monotonic reasoning. So questions like answer set programming and some other sort of non-monotonic reasoning techniques like circumscription you find on the second. Once we get to the polynomial hierarchy and beyond, well, model counting is hard for the polynomial hierarchy, propositional model counting. And we have various PSPACE-complete problems such as planning, modal logic, and quantified Boolean formulas, which is what I'm going to be talking about. So what is a quantified Boolean formula? So we start with propositional logic, and we're going to extend it with quantifiers, but these are going to be Boolean quantifiers. So their range is going to be over 0 and 1. And the way we should interpret this is it's going to be an and or an or, depending on whether it's universal or existential. And these x's here are going to be the propositional variables. So you can see it in here. We connect these a's, b's, and c's via ors, nots, and ands. And they're also the same variables that are being quantified. So it's a bit different from first order logic. A QBF is in premix form if we have this prefix first here, and we have this matrix, which contains all the propositional information. And here we require the matrix to be a conjunctive normal form. And normally we're going to consider only closed QBFs where all the variables are going to be bound in the prefix. And QBF is not just a PSPACE-complete problem, it's also considered the canonical PSPACE-complete problem because it has very nice properties. One of the nice properties is that if you restrict the number of quantifier alternations, you actually end up with complete problems for each of these individual classes. So that's a very nice property of QBF there. Okay, so QBF, we can see our motivation for QBF solving coming from SAT. So SAT is actually just a special case of QBF. It's actually where we've got this on the first level of the hierarchy, and we just have everything existentially quantified. And SAT solvers, we know, are hugely successful, and they can solve instances with millions of variables. And when moving from SAT to QBF, which is what we want to do for solving, we should not really throw away all the advantages that we've learned in SAT. QBF solving should at least start with using the SAT methods as a basis. Okay, and I'm going to go over a sort of naive technique about how you can look at a QBF problem as like a SAT problem. Now, unfortunately, I know I was told that I've got to give you a gentle introduction, and it is 10 a.m. in the morning, but I am going to introduce some proof systems very early on in this talk because we are going to be doing proof complexity, so we need to actually know these proof systems in order to compare them. But first of all, let's just look at this. So this is the definition of how the universal quantifier works in QBF via this sort of expansion over the 0, 1 variables. We can look at like a generic QBF where we have some universal variable in the middle of the prefix here. So pi1 is just the left part of the prefix, and pi2 is just the right part. This u appears somewhere in this propositional matrix, which is going to be a CNF. What we could do is we could actually just expand over this u, just using the definition. We get two sub-QBFs here. Actually, these should not use the same variables, right? It's just sort of bad form to reuse the same variables in the same QBF. So these ones should be labeled differently. Now, in order to keep track of this, in our papers, we like to write it like this, where we actually are saying that this is when we set u equal to 0. This is when we set u equal to 1. This is just a renaming of the variables. In this talk, just to save a bit of space, I'm just going to write them like this. So we're just saying u bar and u, just to save some space. Okay, so we have these two copies of these this sub QBF, and then we can actually just prefix this out because now that they don't share any variables, it doesn't really matter what order we put them in after that. So we can actually just put this as a prefix, and again, now we've just got a CNF here because it's just connecting these two CNFs by an AND. And we can keep on doing this, starting from the innermost universally quantified variable to the outermost, and we end up with an expansion, removing each of the universal variables. So here's an example. Here we've got 5 different variables in our quantified prefix, and those are the 5 variables appearing in our CNF. And we have 2 of them are universal variables. We start with expanding out this d, and then we expand out this b. Now, initially, when we expand out this d, this e gets 2 different copies because it comes afterwards. Once we expand out on the b, the c gets 2 different copies, and the e is now 4 because it's doubling again. And the number of clauses goes from 2 to 8 because we multiply by 4 here. And we can see our various sort of copies, and we keep track of them with these annotations. Now, these contain clauses that have 1s and 0s in them, so we can simplify them. We can remove all the clauses that contain 1. We can remove all the 0 literals as well. And we end up with just a problem that is now a SAT problem. So you could do this for any QBF, and you might be thinking, well, there's an obvious cost to this, and that is that you could start with something, a very succinct QBF, and expand it out to a very large SAT problem. However, in some cases, we can see that in this example, there's not such a problem. So maybe in some cases, we could take advantage of this. So what about like the unsatisfiable case? Well, in the unsatisfiable case, we might be interested in a resolution-based proof system for showing that these QBFs are false. And we could do so via this expansion. So what we do is we basically find these clauses that we could have got in the expansion, but we do it in a lazy way. So we choose some clause in the matrix, and we choose some complete assignment to the universal variables. And we're going to insist, just because of simplification, we'll end up removing some clauses, that this complete assignment will not satisfy any universal literal in that clause. Otherwise, it's just going to simplify it to 1. Therefore, we then derive the clause, which is going to just contain all the existential literals and include their annotations based on this complete assignment. And this is done in a lazy way, so you're not having to do this for every clause. You just, any clause that you require, you can do this. Once we've downloaded all the axioms that we require, we then just proceed with resolution. And in this resolution, the annotation actually defines the variable. So in order to have a resolution pivot, the annotations have to match. Now, this can be very useful because in some cases, you may have a QBF, and it may expand into an exponential size SAT problem if you do this universal expansion. But the contradiction may only require a small number of instantiations of the clauses. However, the opposite can happen. So first of all, I should say that this is the calculus called for all expansion plus resolution. And the weakness of this proof system is that it's vulnerable to semantic lower bounds. So that is where you have a false QBF that may be small, and it expands to a large QBF, and you require an exponential number of clauses just to get the contradiction.
Can I ask you a question?
Sure.
Do you, like, when you do this, do we have to commit to a single tau and then we're going to do the expansion with respect to this tau, or do I get to pick different taus? Because I'm worried about, like, if I get to pick different taus, then I will get smaller clauses from inconsistent taus, and then I'll resolve them to get contradiction. And I'm assuming your proof system forbids that. So which tau can I choose?
You have to pick a complete assignment.
Okay, and one and only one.
For each instantiation of the axiom, right? Okay. You can instantiate an axiom. You can choose a clause, and you can do it multiple times with different taus. Okay. And in fact, sometimes you require that in order to get the contradiction.
Okay.
But these will have different annotated variables, right?
And
okay. When you do the resolution, you require the annotations to match.
Okay, makes sense. Yeah. I missed the annotation part. Yeah. Good, thank you.
And so here's an example where you can see some of that. So for example, in this particular clause here, we're going to instantiate it into the proof system, which is going to continue with resolution. When we do so, we can only pick one universal assignment because we've included all variables in this clause here, and that is to falsify each of these universal variables. And this appears in this annotation of E5. For E2, we only required to put the U1, the negative U1 annotation, because these other variables actually occur afterwards. In the case of this particular clause, we can actually instantiate it in two different ways, or actually we can instantiate it in four different ways, but we're going to use two of them. So here we're going to instantiate it with all the universals being false. And here it's going to have U1 to be false, U3 to be false, but U4 to be true. These sort of clauses can interact with different parts of the proof. And eventually you get these two singleton clauses on this E2, which you resolve to get the empty clause. And the empty clause shows that this QBF is a false QBF. Okay. So this was like very vulnerable to these like semantic lower bounds. And one of the reasons is that you've got the axioms that you have, and you can't really do any sort of inference with them. You have to just translate them into SAT, and this may cause a problem. What if you could actually just sort of modify the QBF that you start with? And this is like on the other side of QBF proof systems and other QBF solving. And it's doing something very similar to expansion, but doing it in a way that preserves the prefix. And this is just for all reduction. So suppose, again, we have a QBF, and we have this universal variable here. Let's say that we start with this clause here, and it's got this universal variable in there. I'm going to claim that you can, in some cases, just drop this universal variable. And that is when all the other variables of this clause, these variables of C, are in the left part of the prefix, so left of U. And the way that you do that is you can do, again, via an expansion. So you do an expansion. You've got clauses, and these simplify. So on the left-hand side, this simplifies to C. On the right-hand side, you can just drop it. But the C can sort of exist outside of this pi2 here, because it's not quantified. It's all quantified inside of this pi1 instead. Therefore, you can sort of take it out and then do things like duplication and duplicate it on either side, and then reconstruct this U just by doing the reverse of this universal expansion to get this derivation here. Okay. And this gives us our next proof system. Again, apologies for introducing two proof systems so early on, called QU resolution. So here it's very simple. You just have an axiom, and it's just a clause as it was before. So it's contains existential and universal variables. But you're going to be able to drop those universal literals later on. And you do this via this reduction rule, which is if you have a universal variable and all the other literals are quantified to the left of it, you can actually just drop that literal, as long as there's no sort of tautology within that clause, because otherwise this doesn't really work. And then resolution just works as before. You don't have any annotations to worry about. It's just dealing with literals. So maybe it's a bit more clear with an example. So here we've got a QU resolution proof, and you can see that the binary rules will be the resolution rules, and the unary rules will be the reduction rules. So in this particular case here, we have this U2 that occurs to the right of all the other variables in the clause. And therefore, you can just drop it. Later on, so for example, here, we have this x3. And this x3 is like blocking this, this U1 and U2 from being reduced. But once you do a resolution step, you actually remove that literal. Therefore, you get a clause that can be reduced. And this is how you proceed in this QU resolution. And once again, the empty clause means that this QBF is false. Okay, so if you didn't understand exactly all the specific details of the calculi, I'm just going to summarize them very quickly here. So both of these are sort of resolution-based proof systems, using resolution as the heart of like the propositional inference. They deal with universal quantifiers in a different way. So expansion uses expansion, and a QU resolution uses reduction. QU resolution has the advantage of being able to work with the original variables, whereas for expansion, you always use existential variables, and you have to include many copies with these annotations. And they actually correspond to different kinds of solvers. So on one side, we have these QCDCL solvers, and on the other side, we have expansion-based solvers. And these solvers turn out to be different depending on how many quantifier alternations that you have. So on the QCDCL side, we're good when we have many quantifier alternations. But on the expansion side, if you have few alternations, and many problems in practice may actually just only have a few alternations, then you have an advantage in solving. And this can sort of be explained, and I won't go into full detail of how this works for these things in blue and red, but I will explain the lower bounds that you get. So I've already briefly explained this semantic lower bound that you get from this expansion side, but you also get lower bounds from circuits on circuit complexity that transfer to proof complexity lower bounds in QU resolution and related QBF proof systems. So before I continue, I'll just summarize what the different kinds of QBF proof systems are. So as I said before, you get this for all expansion lives in here, QU resolution lives in here. And there are other proof systems of these flavors based on various sort of solving techniques or generalizations of the proof systems. We've also studied algebraic proof systems. So that's when we turn things like cutting planes or the polynomial calculus into a QBF proof system. And at the top, we have these strong proof systems. So these are going to be like generalizations of extended Frege, generalizations of DRAT or the secret calculus. And we have known lower bounds for some of these weakest proof systems. And we say that these stronger systems are basically the ones that don't have any known lower bounds. And we have this line about strategy extraction, which I'll explain in a bit. So before we get on to strategy extraction, I should talk about the game semantics for QBF. So I introduced QBF via these quantifiers and what they mean via expansion. There's an alternative way of understanding QBF. And that's only for QBFs that work in this premix form with a conjunctive normal form matrix. So QBF actually will represent a two-player game between an existential player and a universal player. And the game works in the order of the prefix. So you start from left to right in the prefix. Whoever quantifier appears, they get to set a Boolean value for the variable being quantified. And that Boolean value substitutes over the variable in the CNF. And the existential player is trying to choose their values so that the matrix is going to become true. And the universal player is trying to make the matrix become false. A QBF is true if and only if there exists a winning strategy for the existential player, right? So that means no matter what the universal player does, they can always respond in a way that satisfies the matrix. And likewise for falsity. It's false if and only if there's a winning strategy for the universal player. So let's look at an example. Here we've just got this very simple QBF with two quantifiers. The universal player will move first, and they'll choose a value for y. And no matter what they do, they're going to satisfy one of these two clauses, right? Now the existential player can set the value of z, and they can set it in such a way that the other clause is satisfied. Therefore, they win, and therefore this QBF is true. So we have that a QBF is false if and only if there is a winning strategy for the universal player. A QBF is also false if and only if there is a proof in some complete proof system. Can we match these two things? And the answer is yes, sometimes. This is when a QBF proof system has the property of strategy extraction. So if we have a QBF and a refutation, can we, in polynomial time, extract out circuits that represent the strategy for the universal player? And these strategy circuits are going to output some Boolean value for each of the universal variables. And they're only going to take variables to the left of you in the prefix as their inputs. And if we actually took the strategy circuits and plugged them back into the formula in place of the universal variables, we're going to end up with a false propositional circuit, or an unsatisfiable propositional circuit. So which proof systems have this strategy extraction property? Well, for the proof systems that use resolution, we can actually prove the strategy extraction in a similar way to how feasible interpolation is proven for propositional logic. So what you do is you put yourself in the perspective of the universal player, and you're equipped with this proof that is like a resolution proof. And you observe what the existential player is doing on a particular turn, and they're going to assign some values for the outer existential variables. When you do that, you can actually then update the proof, restrict it with those existential variable values, and it then becomes obvious what what your outer block of universal variables should be in order to continue to restrict this proof. So you extract out your response, and then you plug it back into the restricted proof, and you just keep on iterating until you reach a restricted proof of where everyone has played their games, in which case it must be that a clause is falsified. For QU resolution, there's also a different technique, and this has the advantage that we can actually allow bounded depth circuit strategies. So in this technique, we have this reduction rule, right, where you dropped a universal literal. We're going to observe the entire proof and start at the bottom of the proof, where we've got the empty clause, and construct a strategy backwards so that it works for the original clauses. And say we have a strategy that works when we have derived C. Can we derive a strategy when instead we had C or U? And that is to say, well, if C is false, then we set the value of U to be 0. Otherwise, we play the old strategy. And in this way, we can actually construct a decision list moving backwards in the proof for each of the universal variables. And a decision list is actually a bounded depth circuit. You can write it in this way here. Okay, so that allows me to move on to using this idea for lower bounds. So now we're going to connect circuit complexity for bounded depth circuits to lower bounds for QBF proof systems. So first, we're going to come up with a family of QBFs that are going to have some strategy that is going to be hard for bounded depth circuits. So the way that we do this is we have some Boolean function. We encode this particular QBF that is stating that some universal variable does not equal this Boolean function. These extra variables T are going to just help describe the computation of the circuit in CNF. And this QBF is false, but it has only one strategy for the universal player, and that is to play Z to equal this Boolean function. If we have that this function is going to be the parity function, then it requires the strategy will have to be parity. So this gives us our lower bound, because provided the strategy extraction property, if we start with a short proof, we must have a short strategy. If we have a long proof, well, it's still polynomial time, so it could be a short strategy or it could be a long strategy. But the key is that long strategies only come from long proofs. So if you have the strategy of that computes the parity, if it's a bounded depth circuit, well, it cannot be written in a polynomial size circuit if it's bounded depth. Therefore, in QU resolution, the proof of Q parity, the refutation of Q parity, must be large. In fact, parity requires exponential size circuits in bounded depth formulas. Therefore, Q parity has an exponential size lower bound for QU resolution. And this is actually a general technique that can transfer circuit lower bounds in order to proof lower bounds for QBFs. So we have problems like the Q parity formula. How do we get around that perhaps in practice or like a certification setting? Well, we can use things like the extension rule, right? So the extension rule is where we have a new variable that defines a Boolean function on existing variables. So here we have just the NAND, because NAND is functionally complete. And in propositional logic, we can combine this with resolution to get a very powerful extended resolution proof system. And extended resolution has no known lower bounds to this date. Yeah.
Question. So earlier you said the Q system is worse when you have few quantifiers.
Yeah.
It's worse than the expansion-based systems. Is that something that we should be seeing from the circuit characterization you just gave, or is that just like kind of a practical statement?
It's both. Yes, experiments have been done that have shown this on various benchmarks, that on lower number of alternations, you get that. But also that is an example of something that has just got like three quantifier levels, and you can then get this lower bound. And you can't do that so easily in this expansion base.
In the expansion.
Yeah.
Okay, perfect.
Yeah, I think there are examples where you can get the lower bounds for just a small number of levels, but not using that specific technique. Okay, so we have this extended resolution is very powerful. What happens when we try and put this extension rule in QBF? Well, we actually have to put the extension variable somewhere in the prefix, right? And we have to give it a quantifier. We always give it an existential quantifier. And originally, it was proposed that we always put this extension variable at the end, right? This is kind of the safest way to do it. But that's not the most powerful way of using it. In fact, it's actually sound to put it just after the variables it's being defined. There's an exponential improvement when you do it. So there are formulas that require exponential size if you put it at the end, but you have short proofs when you put it early. And this would be the extended QU resolution system. Extended QU resolution, it says here. So you have an axiom, extension, resolution, and then a reduction.
So it's always better to put some more?
Yeah. Because you can then do more reduction steps, because it's an existential variable, right? So what it does in the proof is that it's actually going to block universal reductions. Mm-hmm. So if you put it earlier, you block fewer reductions, and you want to be able to use reductions as early as possible. Okay, yes. So this extended QU resolution actually does have this strategy extraction property, and it has this property similar to QU resolution, because extended QU resolution is just a QU resolution proof where you can do all the extension steps right at the beginning of the proof, right? So the rest of the proof is just going to be a QU resolution proof, and then you can just do the same decision list construction that you did before. The only difference is that your decision lists will now depend on extension variables rather than the original variables. So what you do in that case is you replace your extension variables with just the circuits that they represent. Because when you do an extension, you're actually just creating like a circuit that computes a function on the original variables. So you get like a p-poly decision list, which is really just equivalent to a p-poly circuit. Therefore, you're not going to get an unconditional lower bound, but you do get a conditional lower bound that if there's some function that is contained in p-space, but not in p-poly, then you can construct this lower bound by QF. So these like Q parity, but with some function here. What's more interesting is there's a kind of like a converse to this as well, which I'm going to get onto. Okay, so remember that when we have the strategies for the universal variables, if we substitute them back into the matrix, we actually get a purely propositional statement that is also unsatisfiable. When we get to that, we can start thinking about our propositional proof systems. So it turns out that you can transform extended QU resolution proofs such that the first part of the proof is going to be purely propositional, and it's going to basically state that this particular thing here is going to be false, right? And you do that by extracting out the strategies and then sort of substituting them in and then proving this sort of thing here. And then from that, you derive, just using extended resolution, that at least one universal variable does not equal its strategy, right? Because if you start with the matrix and you know that the matrix substituted, where you substituted the strategies is going to be false, the only course of action is that one of these universal variables is not going to equal their strategies. But once we arrive at this, it's actually very simple to just use universal reduction in a very uniform way in order to reach the empty clause. I'll show you how this is done here. So you have a disjunction like this. And this disjunction will be written with extension variables. And in a simplified way, what you end up doing is you do for reduction in both directions. And you can do this because your last variable, your un, actually there's no other variables in this formula that are to the right of it, because all the strategies always depend on variables to the left of each of these things. And for your last variable, there's nothing afterwards. When you do that, you actually get these two different disjuncts on this side, which effectively you can resolve together. And at that point, you've reduced, like you've removed one of these disjuncts, and you can just repeat this until you reach the empty disjunction, which gives you the empty clause. And this gives us our nice lower bound characterization. So extended QU resolution has a lower bound if and only if either extended resolution has a lower bound or p-space is not contained in p-poly. So the backwards direction, suppose we have a function that is in p-space but not in p-poly, then we can construct these QFs that give us this strategy extraction lower bound. Also, if you have an extended resolution lower bound, we can just write this as a QBF. And because this contains no universal variables, we're never doing universal reduction, so it's an extended resolution proof. In the forward direction, now suppose we have some lower bound for extended QU resolution. We're going to look at the shortest refutation and convert it into a normal form, which means that we do all these propositional steps first, which prove this particular thing here. Now, either this particular expression here is going to be big or it's going to be small. If it's going to remain small in the size of the original QBF, our lower bound could only come from this having a long proof in extended resolution or extended Frege. Therefore, we show a propositional lower bound. Now, if this thing is big, that could only happen because one of these strategies or some of these strategies end up being large, which then gives us our circuit lower bound. Okay, so this has like quite a nice sort of like property because it means that like we're not expected to find lower bounds for this extended QU resolution because it implies a disjunction of two. Here is an open proof complexity problem, and here is an open circuit complexity problem. Right, and talking about the strength of extended QU resolution leads on to this next section about using strategy extraction for P simulation. So a P simulation is a polynomial time mapping from a weaker proof system to a stronger proof system. It's some function that maps G proofs to F proofs and it preserves a theorem. So recall again that if we have this particular, if a false QBF, we have the strategies for each of the universal variables, we can substitute this in. The important part of this slide is I've just named this thing as phi strat, where phi was the matrix. And again, we can use it, we can just sort of refute that part in extended resolution. So suppose we have some QBF proof system. I'm just going to call it S. I'm going to say that S has strategy extraction, right? If it has strategy extractions, we know that this particular small version of the matrix is going to be false. Because this thing is false, it will have an extended resolution proof. We don't necessarily know how to find that, but it will have one. Now we can sort of like think about simulating this by extended QU resolution. So in extended QU resolution, you're allowed to take the clauses of the matrix as axioms. And once you do that, you can derive this disjunction here. And then you can proceed via this normal form method until you reach the empty clause. So this almost what we've got is we start with an S proof and we end up with an extended QU resolution proof, which is almost like a P simulation. The only missing part is how to get this extended resolution proof. And the idea is that we observe the structure of this S proof in order to construct this extended resolution proof. And this is exactly what we do. So we've now shown that extended QU resolution actually will simulate all these various different proof systems. So if you see here, here's our for all expansion plus resolution, which is the proof system that I started with. And then you've got QU resolution here, which is simulated by other systems, which we've shown this simulation. And all these simulations are done via this strategy extraction technique. So it ends up being very powerful. So how do we do this, like, for example, for this for all expansion plus resolution technique? Well, what it was shown, well, while I was coming up with sort of general technique, I didn't have any examples of it. Schaefer et al., including Friedrich Slavoski, showed that every clause in for all expansion plus resolution has like a local strategy. So this is like a strategy that if combined with the original propositional matrix sort of affirms each clause. Now, if you remember, for all expansion plus resolution actually didn't have ordinary clauses. It had these like annotated literals. So in fact, in their paper, they make some sort of like I call it like a propositional conversion of these annotated literals. But it works when we do that. And when you have the final strategy, you're actually just affirming the empty clause. So you're basically suggesting that this your matrix is false. So because we have the local strategies for each of the individual clauses, we can kind of just like look at the proof inductively from the axioms to the empty clause and look at how the local strategies are built and sort of just build them ourselves, doing it in a formal way in extended Frege or in extended resolution. And that's how we end up with this P simulation. And this sort of generalizes to the stronger versions of for expansion plus resolution. So this one here and this one here. How much time do I have?
Well, I mean, for the first half, but say 10 to 15 minutes more.
Okay, well, in that case, I might just finish this section then, and then we can have the next part for the next section. Okay, so yes, so this for expansion plus resolution actually generalizes to some stronger proof systems as well. And we managed to show, first of all, we managed to show extended Q resolution simulates this, and then just generalize that up. For some reason, this IRM calculus is, this local strategy extraction also works with this very different proof system over here. So we managed to look at some papers and just sort of convert our simulation argument from this one to this one here. The big problem case was this long distance Q resolution with dependency scheme in them, because we've put so many parts into this particular proof system that getting this local strategy became very problematic. So what I ended up doing, and it took a lot of work, is we had this other kind of strategy extraction. If you remember back, we had this round-based strategy extraction, which is very similar to feasible interpolation. And I ended up having to formalize that all with extension variables in order to show that you can P simulate it. But it did end up working out, and we do get the P simulation. So another way of putting this technique is to talk about it just sort of generally, and I've just called this optimality modulo NP among the proof systems that have strategy extraction. So we've created something here that is not technically a proof system. So we have extended Q resolution, and we introduce a new rule which says that if something is just propositionally implied, you can just derive it in one step, right? And the reason that we do this is because we're in a QBF setting. We're not really too interested in propositional difficulty. So when you add this extra rule, you can actually just do this step for free. And it means that this particular proof system will be optimal among all the proof systems that have strategy extraction, because you can simulate them. Now, finally, I want to just talk about something a bit new. So we found this extended Q resolution, and it's also, I should say, it's this, we call it extended Frege plus Fourier reduction as well, because just like in propositional logic, extended resolution and extended Frege are basically the same proof system when we're talking about P simulations. Extended Q resolution and extended Frege plus a Fourier reduction rule are the same. But essentially, this calculus is really quite simple. All it is if you can guess the strategy circuits and find an extended resolution proof confirming them, then that actually just gives you this extended Q resolution proof. It's very easy to construct, especially when you see it in this normal form. And this extended Q resolution proof system, it doesn't have lower bounds unless you solve some open problems. So it's actually really powerful. So can we just sort of do this? Because this works in QBF, can we just do this for other P-space languages as well? And it seems as though we can. For model counting, we tried exactly this sort of thing. Instead of using a multi-circuits for the strategies, we had a multi-circuit that actually does cumulative counting on the number of models as you progress through like some lexicographic ordering of the models. And then you could just sort of confirm using induction that this cumulative count is correct. And this ends up with a proof system, which is called CLIP, which has the same properties that extended QU resolution does, right? You can't show a lower bound easily for this proof system. And I'm thinking about this, and I realized that the only thing that we used here was that the fact that it was in PSPACE. So it turns out that for any PSPACE language, you can get a multi-circuit that calculates the memory over time of like some algorithm that runs using polynomial space. And the memory is always going to be less than polynomial, right? And then you can sort of confirm it inductively with the extended resolution, and you end up with a proof system that has all these nice properties that we have in QBF as well. So this is the proof system clip, and it's sort of parameterized by some propositional proof system P and an algorithm that runs in polynomial space A. So this algorithm is, think of it as on a Turing machine. We have a transition function from one state to another, and we want to sort of calculate how the memory is running over time, and we use a multi-circuit. So the input is going to be time, and the output is going to be how the memory is. And we're going to represent it with this circuit here. And the statement of correctness is saying that for any time point, if we increase the time point by 1, it's going to respect the transition function. That's all that we're saying here. And this is actually just in co-NP, right? Because the time is going to be bounded above exponentially, right? Which means that if we take a logarithm of it, it's small. And the output is going to be bounded above polynomially because we're in PSPACE, right? And we can also do this with non-determinism as well, because NP space equals PSPACE. And yeah, this is the, and then we just sort of confirm this co-NP statement using some propositional proof system. We just pick the strongest proof system that we want. So for example, extended resolution. And we get the same sort of result that we do in extended QU resolution. So for any decision algorithm, then if we equip this with a powerful proof system like extended resolution, it has a super polynomial lower bound only if extended Frege has a super polynomial lower bound or PSPACE is not contained in P-poly. So suppose we have a super polynomial lower bound. The memory over time is still in PSPACE, and now we suppose that PSPACE is contained in P-poly, then our memory time circuit is going to be small because of this complexity assumption here. And then we have this induction step verifying that this thing is true. And this is all the actual statement of this co-NP statement is also going to be small as well. Therefore, it must be a super polynomial lower bound for extended resolution. And I think, do we have more time, or should we?
We're at your disposal. I mean, you can paste the seminar as you like.
I think this is a good place to stop because we've got some more difficult material coming up. So I guess there's questions now, or is that?
Yes, questions. I mean, thanks for the first time. Yes.
Do we have any solvers or proof systems trying to combine the Fourier expansion resolution and the Q resolution?
Yes. So there's this cake system by Leander Tentrop, which does combine this in like a Seeger algorithm. So the original cake was very much doing what Q resolution, which is the weaker form of QU resolution, was doing. And it added some other things as well. And then it realized it had this weakness that it couldn't do this expansion stuff. But because it was using the Seeger loop, it was very easy for them to just add expansion in that. And it's one of the better solvers. So yeah, but more sort of understanding needs to be done about what's happening in this cake algorithm. As I said, yeah, it's not very well understood what this algorithm is doing, but it is using some combination of these things.
In terms of proof systems, like the best that we know, I guess both of them are in extended QU resolution. That's the best that we know about the combined proof system, or? As
I said, we don't really know about this particular solver. This IR calculus is like a combination of this Q resolution with this Fourier expansion plus resolution. Now, this Q resolution is because of how the solvers work, they never actually do resolution steps on universal variables. So the resolution steps are always going to be existential variables, which is what this Q resolution does. QU resolution is actually simpler for me to state because it's just saying resolution can be any pivot. But when we don't allow those universal variables to be resolved, we get this IR calc, which is the motivation of IR calc. But no solvers really use IR calc to its full potential.
What about the strategy extraction? So we expect that strong systems, like if you get too strong, you want that strategy extraction?
Yes. So if you can stick around for the next part of the talk, I've got some examples of that. Yeah.
Maybe another question is, so in general, I feel like in complexity theory, sometimes it's much easier to prove a disjunction. So why do we believe that your particular disjunction is like a disjunction between two operos can be much easier to prove than those separately? Like, is it because they're from two different fields, or is there some other reason why we believe that this particular disjunction is not?
I think I was just being careful. I don't think it's necessarily easy to show the disjunction of these two complexity problems, right? You're talking about the two open problems.
The lower bounds for extended resolution and the separate, like the P-space and P-poly.
Yeah, so I think incorrectly before I stated it as like, oh, you can't solve this problem without solving either one of these two problems, right? But like to be safest, you say you can't solve it without solving the disjunction of these two problems, right? So I was just being careful.
Yeah, no, so what I mean is that, but do we have a good reason to believe that in this particular case, this disjunction is not much easier to prove than by proving one of the two?
I don't know. Like these are very difficult questions to answer.
Okay, so let's thank Leroy again. So we are back after the break, and Leroy will continue, please.
Okay, so I left you on this little diagram here where we looked at some various simulations. We looked at the simulations of extended QU resolution. It has this nice sort of umbrella effect over these things here. So in this part of the talk, I'm going to go into a bit more details about how it simulates these particular proof systems in green. And then we're going to move on to the next section where we're going to talk about these proof systems in blue and their various relations. Okay. So first of all, I talked about this local strategy extraction, but I didn't give any details. So I said that we simulate this full expansion plus resolution. And the problem was that this had these annotated clauses. And I promised a propositional conversion of them. So the propositional conversion is simply you just take a conjunction of the literal and its various literal annotations. Now, this should not be treated as like the official interpretation of these clauses. This only works when you're applying a local strategy. So what does that mean? Well, you have some sort of insistent on the universal variables represented as like a propositional formula, S, which is stating that U equals true or false or whatever. And then you take a conjunction of that with the matrix, and it insists on this propositional conversion of this clause. So the local strategy extraction result is that every clause in the proof has this particular result. And so what we do when we simulate it is we're proving each of these individual lines inductively in the shape of the proof. So we start with the axioms. And for the axioms, the actual strategies are just going to be the complete assignments. So remember back to the definition of full expansion plus resolution. It was like an hour ago, but it was that we took a clause and we took its assignment to the universal variables, and we did like an instantiation on that particular clause, which removed the universal literals and annotated the existential ones. And for the axioms, that universal assignment will just be the local strategy. For the resolution step, well, it turned out that Suter and Glaise had already kind of investigated this when they were trying to interpret what a full expansion plus resolution proof was doing. And that is by this combine operation. So you have two clauses which you resolve over some pivot x u bar v. And on this clause, you have a left strategy, and on the other clause, you have a right strategy. So those are the local strategies. And your new strategy is going to have to pick between L or R, depending on what happens. What it does is if it can guarantee that this particular clause will not be satisfied, then you can pick L, because it means, sorry, this particular conjunction is not satisfied. It means that in this particular clause, one of these two things would be satisfied, and likewise with R. And it can do this in advance in respect of the ordering as well. So what we did is we just sort of formalized this all within propositional logic, and that gave us our P simulation by using this whole technique. What about these other proof systems? Well, I haven't properly defined them, but the idea is that for expansion, uses these complete assignments and complete annotations at the axiom level. In the IR calculus, what you could do is you can delay the annotations or the assignments. So you conservatively give the clauses annotations, and then you can perform instantiations in later steps. So you're working with partial annotations. And for IRM calculus, it expands this even further, because you have both partial annotations and ambiguous annotations. So this is saying that some value has been set, but we're not specifying which value it's going to be. And in each of these cases, there's exponential gaps between each of these proof systems.
Do we need to understand this? Because this is a little bit hard. I am not understanding.
I'll give you an example of the IR calculus.
Okay.
Yep.
The exponential gaps.
So there's formulas that are, so there's a P simulation, and there's formulas that are hard for this this proof system that are easy for this one.
Okay, so we have lower, these are the ones we have lower ones.
We have lower ones for these, yes. Okay, so this was our example for expansion plus resolution. And if we look at these particular axioms here, we get like 2 different copies of them when we do our axiom rule, which we use in the resolution proof. And then we derive, using them, we actually derive very similar clauses later on. We derive this sort of not E5 singleton clauses with these different annotations. So what we do in IR calculus is we just sort of do a partial instantiation very early on just to remove this universal literal. So we're still working where we have purely existential clauses. Now we've got these partial annotations. We can actually just resolve these 2 here. We get this single clause here, which we then instantiate to those clauses that we find later. So in this sense, we're actually just, if we have very DAG-like proofs, we can actually sort of take advantage of that in this IR proof. So if you have a tree-like IR proof and a tree-like for all expansion proof, they're actually just the same thing. So it's really just taking advantage of this sort of DAG-like thing via this sort of partial annotations. IRM calc, it's a bit too complicated for me.
What was ambiguous part?
So you have here that, for example, this U3, it's set to some value, so it's not like missing from the partial thing. But you sort of just say that without giving it a particular value.
Without giving U3 a value, or?
So you say that it's been set, so you can get to this point here where it's been set here, and then just say, oh, I'm going to forget that it was set to 0 or 1. Right? And in this way, we can sort of like maybe save the number of literals that we use in a particular clause. So you might have, you can have clauses that contain maybe the same literal, the same base existential literal with different annotations.
Do you have the previous example?
Yeah, sure.
So, because basically, I mean, but there you're labeling E5 with. Oh, now I'm confused.
So for expansion, you have to give a complete assignment straight away, right?
But that's just because that's the way it was
That's
decided.
the way it's defined, and that's also the way that the solver was working.
Okay, so that's what, because it's like so IR is basically saying, well, why do you force me to give away the full assignment right away?
Yeah.
Let me focus on U4 for now, and we'll talk about the rest.
Yeah, exactly. Because if we can derive something via a complete assignment, it may be that some of the values of those complete assignments were completely irrelevant to those derivations.
Yes.
So IR calc is sort of like saving us and saying like, oh, we could derive this, therefore we could have derived all these other things as well using the same resolution steps.
Mhm.
Okay. So yeah, again, so this is the same proof almost, right? It's just saving us repeating this step for E5 in these cases. We just do one resolution step here instead of doing two separate ones, which then and then we sort of split off at this point. Yeah. Okay, so it gets a bit more complicated when we try and simulate this using local strategies. Now we have to move from local strategies to local policies. So this is just partial strategies. So we actually need to specify using circuits whether a particular strategy is setting a value or not. And we just construct this with circuitry extension variables. And it means that our propositional conversion changes as well. So suppose we have some literal E, and the variable comes after U, V, and W. Then in the old proof system, we would have an assignment to all those variables. In this case, we could have like a literal that is missing U, its annotation, right? And in that case, the propositional conversion, well, it has to be respect to a particular strategy, and you specify that the set thing is false for U, and it's true for V and W, and you also give the values here as well. And then we just have to do the hard work of simulating this in propositional logic. For IRM calc, the interpretation that you will make actually is very conveniently, you just actually, for these ambiguous annotations, you just specify the set value, but you don't give the value here. And that also works out very nicely. And because Suter and Glaise wrote this combined framework for IRM and also this LQU plus, with some work, we managed to convert this P simulation of the IRM calculus to LQU plus as well. Okay, so that's just the hard details of that particular section, which I wanted to put over here. So now let's talk about proof systems without strategy extraction. So I am going to talk a bit about QRAT here, which is has many moving parts to it. These are the rules of QRAT. So I've tried to simplify them down to just saying it's sort of logical rules. So that's just adding clauses when they're propositionally implied. There's some block clause addition that you do. And there's this version of universal reduction called extended universal reduction. And actually, this extended universal reduction is like the block clause addition is quite difficult to understand, but this extended universal reduction causes a lot of problems when looking at the proof.
So coming from a propositional point of view, block clause addition would be some special case of the RAT rule?
It's the QBF case of the RAT rule, basically.
Okay.
Yeah.
Because, I mean, in the propositional setting, block clause addition would be a special case, but here it's kind of the general case. Or you'll tell us, I guess.
Oh, I was just simplifying things down for this slide. This is just basically, you can think of this as RAT, but if you never came across RAT before, I'd say,
fair enough. Yes, sure.
Okay, so what is a quantified resolution asymmetric tautology? Now, if you're familiar with RAT, this is the part that is different. And that is, so normally when you did this sort of block clause addition that you do in RAT, you have a clause that you want to maybe add or remove, and you have all these other clauses that you need to check it against, so the clauses that contain the negative literal. In the QBF version, you have to actually respect the quantifier order. And to do this, we need the definition of like an outer clause. So suppose we have some D with a negative literal in it. The outer clause with respect to this literal is going to be the subset that is left of that literal, and maybe including the same block as well, but not including the variable. And then the QRAT property is we have some clause.
So all earlier quantified literals.
Yeah. So
literal.
yeah.
Okay.
Yeah. So the QRAT property is for some clause with respect to some matrix and some particular literal, existential literal within that clause. We have that if we take the formula and we take the negation of the clause, including the literal, and we take the negation of the outer clause, which is the different part to RAT, then we can, by unit propagation, derive the empty clause. And here, the unit propagation, we're just talking about propositional logic.
And just to clarify, rat here would have inserted all of D, not just the outer part.
Yes.
Okay, so you're asking a little bit more from us. We're not allowed to use all of D, but only the outer part of D.
So if you think of this like extension, right? When you do an extension via, you were adding, say, extension clauses, right?
Okay.
They can depend on variables anywhere in the original rat or the original extended resolution. In QBF, extension always comes like after, you always introduce a variable and it's dependent on variables before. So it's kind of doing that sort of thing in a QBF setting, in a rat setting. So if you started to look at variables to the right of it, you could sort of break this this convention over extension and make things unsound.
I mean, I'm syntactically parsing the definition. I don't immediately see how I could cheat by picking all of D instead of outer D, but that's, you know, I maybe need some time to digest this. That's fine. So we can, I mean, yes.
Well,
definition is clear.
Okay, well, yeah. So in the extension, if you pick something too early in the quantified prefix, you're actually forcing the existential player to compute a function of variables that haven't been assigned yet, right? And at that point, it sort of makes it easier for the universal player because you're committing the existential player to something they shouldn't be able to know it.
Thank you. This was helpful. Yes. Okay. Which means that, and here making the universal player's life too easy means actually switching something that was true to something that is now false. So introducing a clause C that is too strong, too good to be true.
Yeah.
Okay. Yes.
Okay, and the QRat addition is suppose we have a clause with QRat with respect to this existential variable. Then we can add it to the clause, and we might add new variables in this way, and we could simulate extension variables as we defined it before. Okay, so what's the intuition behind this? So suppose we have that this thing is true, then we need to show that this thing with the added clause is also true as well, but we can also show it the other way around. So suppose this thing is false, then this thing is false. So suppose we have some universal strategy from here. We want to produce a strategy for removing C. So let's say we have the circuits, and we only need to change our strategy under the game when our previous strategy only falsifies C, right? So how do we do this? Well, if the outer clause of some D with this negative literal is false, we don't actually need to change the strategy, right? Because of our QRat condition. Right? Because if it falsified C, then it would lead to a contradiction. Now, if all the outer clauses are satisfied, then it actually gives us a simplification of what the existential player can do. So it means that the existential player can play L as if it was true without costing them any potential clauses that they could have satisfied, right? Because all the clauses, all the outer clauses where we have this potential of it setting it false for the existential player have already been satisfied. So what we do as a universal player is we just play as if the existential player has done this more beneficial strategy of setting L to true. And in that case, we already know under our old assignment, or under our old strategy, in that scenario, we should win because we assume we have a winning strategy. We could also think of this from the perspective of the existential player, and that is to move from here. If we have a strategy from here, to move to a strategy from that, and that is that we play. We just change the strategy for the L variable, which is an existential variable, to be to favor truth in the case that all the outer clauses are satisfied as well. So that also, you get these two interpretations of strategy extraction of why this thing is sound.
Is it correct to say, again, this is going a little bit too fast for me, but that's fine. I mean, we have limited time, but this is sort of the same flipping argument as for standard rat.
Yes. So I think
If I will, like, if I had a few minutes and then.
So there's this paper on simulating DRAT by extended resolution.
Mm-hmm.
And I think they use this sort of conversion here, except this is now just D instead of just the outer clause of D. I think it's D with L removed, right? And you define these extension variables and you replace them.
I guess this also raises the question, did people start to look at like propagation redundancy and substitution redundancy in the QBF setting?
So when I worked with Marine, this was kind of the task I was given.
Yes.
But then I realized there's actually a load of problems with the original QRAD. So I'm more interested in solving those problems before we start to think about, better versions of
really?
going up this ladder. And yeah, I'll get to some of these problems in this talk, hopefully. Right, so this is actually sort of like the nice behaving part of QRAD because it has this little like strategy extraction thing that you can construct. The other part, the problem part, is this extended universal reduction. So how does this work? And I don't even have time to describe this fully. So before we had this universal reduction with the side condition that this C just contained variables to the left of you. In extended universal reduction, you're actually allowed to do it when you have these blocking literals. But the idea is that you have a sense of locality of other clauses, and if universal literal not U does not appear in that sort of local sense, then it's kind of locally pure, and you can do some sort of like pure literal elimination on the universal variable. And the way that you connect things is by resolution paths. So here we have this particular clause with these blocking literals A and D, right? But if we try to create a resolution path to any of the other clauses, we never reach a clause that contains not U here, right? Now, there's a special case in here as well. You notice that we can actually reach this clause from here and this clause from here. But we create a rule that says that actually you can't use the same entry literal as the exit literal, therefore you can't actually form a path here. And this is all QBF theory about dependency schemes and paths here. But the idea is that like in the actual section that it matters, then U is actually pure. And if U is pure in a QBF, then you can just, as universal player, just set it to false. So it turns out that
locally in this clause only.
Yeah, so the way that we use resolution paths is it's kind of saying that if we assigned all the outer variables before U, we've got a remaining QBF, and if this QBF is false, it has a Q resolution refutation. And if the disconnect between the resolution paths means that your Q resolution refutation is either going to be like if it's going to contain this clause, it's going to only contain connected clauses from this local section here, because the resolution path is just telling us like that these clauses can be connected in a resolution. Okay. So it's using the completeness of the Q resolution. Yes, so this is quite a complicated rule. And it causes a lot of problems because it means that we don't actually have strategy extraction.
And are solvers doing that?
Solvers like dep QBF are using this sort of dependency scheme in order to do some solving. But it doesn't cause a problem with the strategy extraction in that because of the underlying resolution proof system. So remember earlier I said that you can do strategy extraction if you have an underlying resolution proof system by feasible interpolation, right? The problem happens when you don't have feasible interpolation. So if you're combining extension and being able to simulate Frege systems, then you start to run into problems. Anyway, it's okay for me to talk about.
Yeah, please.
Yep. So this is an example of where strategy extraction like I call this like strategy extraction edge case. So this is a very easy thing to describe. It's like a chess game. So suppose you're playing against two grandmasters at once, right? On one side you're playing as black, and the other side you're playing as white. You can actually guarantee that you won't lose one of these games of chess, right? And some of you have already figured out how you can do this, right? So you let your white opponent move first, and then you just copy that move over to the other side. Then your black opponent will respond, and then you just copy that. So effectively you factor yourself out of this chess game, and you're guaranteed to win one of them or draw both. And we can sort of understand this idea in special QBFs. So first of all, we're going to create a QBF with a p-space hard strategy, or a family of QBFs with p-space hard strategies. And that is that we just say that we have a universal variable. We say for all u, and we say u if and only if some QBF is false, right? This QBF is always going to be false, right? Because you can always play u to equal the value of that closed QBF. Right? But the strategy is going to be p-space hard in general, because this is a QBF. And you can encode it in this certain way, and you encode it in a very similar way to how you do this, this chess problem in a premix form. Right? You always have that the universal player gets to move afterwards. In this case, it means that selecting this u is the only hard strategy for the universal player, because for all the other variables, you're just kind of copying what the opponent is doing. And now we're not playing over chess, we're just playing over the QBF game. But it's very easy to just use expansion on this u in order to end up with something that has an easy strategy, right? So before we had u in these particular clauses here, and this is just encoding this if and only if this thing is not true. And now we can actually just, if we just expand these things out, we actually remove these various u's. And we end up with something where the strategy is easy because you're just copying the opponent, like in this chess game. And QRAT can do extended universal reduction, which can do the same sort of thing. It could also do expansion by simulating it as well. So because this particular QBF has an easy strategy, we can just do what we did for extended QU resolution and plug in those strategies and then sort of solve this in extended resolution, or in Frege in this case. And get these very easy derivations. And we can simulate all those rules in QRAT as well. So it means that we have short uniform proofs in QRAT and some other things as well. So the SQL calculus, and if we added reduction and expansion to a Frege system as well. So all of these cannot have strategy extraction unless P equals P space. So it's P because these proofs are uniform as well. And the reason is because it's sort of being able to simulate Frege, and Frege doesn't have this feasible interpolation property. If you, this expansion is causing this problems, but if you have it with a propositional proof system that allows feasible interpolation, you still have strategy extraction. So for example, in full expansion plus resolution.
So if Frege did have feasible interpolation?
What?
If Frege did have feasible interpolation?
Yeah.
What are we like? Does the hardness results now for physical interpretation in Frege are cryptographic hardness that you're getting like equals space?
Let me think about that. Yeah, maybe I've simplified what's being stated here a bit too much, I think. So if Frege would you still get these uniform proofs?
Like it takes more than just this.
Yeah, I think that's what I mean. It's I've just kind of simplified it down to say feasible interpolation. What I really mean is a technique that you can use very similar to how feasible interpolation can be. And if you combine that with quantifier expansion, you get this. Yeah. Okay, so I've introduced the first problem proof system, which is QRAT. You also get a problem when you look at G, because G is very powerful. So what you might notice is a bit different is well, first of all, let's just talk about G. It's going to have all the propositional rules that define your various connectives, right? So if any of you have seen the sequent calculus before, you just have, so this is sequent here, your left-hand side implies the right-hand side, and the left-hand side should be interpreted as a conjunction. The right-hand side should be interpreted as a disjunction. And you have rules that define your ands, your ors, your nots. And those are all included here. You have this cut rule. Now for the QBF, you can actually cut over QBFs, which you can't do in this extended QU resolution. And the reason I say that you can't do it in extended QU resolution is that your variables that you do resolution on are similar to like what you're doing cut over. But you're actually only cutting over circuits because the extension can give you the power of circuits, but not generally the power of QBFs as well. So G allows you to cut over QBFs, and it also allows you to introduce quantifiers by sort of like by using some sort of QBF substitution. So if you look at this particular one here, if you're introducing the existential quantifier, you can use this B here as a witness for it. And this B can actually be anything. So it could be a QBF. So in this sense, it's doing a lot more powerful work because this is actually really sort of the reduction rule in reverse. You can see it over here. And in reduction, you actually just sort of take your X and you substitute it in 0, 1. Here it's saying, oh, it can be any QBF, which is much more powerful. And in this way, because G can cut over QBFs and introduce quantifiers over QBFs, it's powerful enough to simulate QRAT, even this problem with extended universal reduction. For the block clause addition, it's not, so for like the QRAT rules, the QRAT addition, it's not too hard because we can just use the same technique as before. We can simulate via strategy extraction, right? So for each of these rules here, we just actually compute how the strategy is modified and express that using circuits or formulas. For the extended universal reduction rule, we can actually kind of use the same thing, but we express strategies using QBFs rather than using circuits. And so the essential thing that we have to prove in order to do that is to show that these sort of like local parts of the CNF actually kind of respect how the QBF works. So here we're saying that if our formula is false, then there is falsity either entirely in one local part or in the remaining part instead, where these are different path reachable components. So for QRAT R, we do exactly as we described. We define a replacement for the existential variables, and we actually just prove that under that replacement you get propositional implication. And once we do that, our quantifier introduction rule allows us just to remove this L dash and give it the name of any eventually quantified variable. What about this extended universal reduction? So suppose we have this clause here where we want to do a extended universal reduction, and this universal variable is somewhere in between on the prefix. We're going to use quantified witnesses to ask whether this connected component allows us to make a case for setting U to equal to 0. But we want to have some sort of independence as a way of showing that this CU is irrelevant to all the other cases of U, where we set it to true. And we're then going to prove this particular sequence, which is sort of just like the reverse of the one I showed before. It's saying that if this is true and this is true, then the whole thing is true for these different path connected components. So here's an example. We have this U that is contained in here, and we're connected up to there. And as I should have explained this a bit further, this X2 is going to be the sub-CNF containing everything outside of this path. And we're just going to observe that here, which will be these two clauses. These may connect to these clauses here, so you actually have this awkward intersection. But this allows you to create like a replacement scheme for each of these variables. What you do is, these are two different independent things in our sequence here. So we actually give the variables different names for these inner variables. For this one, we just give them this annotation, and this annotation will be explained a bit later. Then what we need to do is we need to show this right-hand side. So we need something from here and here that's going to propositionally imply something on the right-hand side. And it ends up being this replacement scheme, which respects this intersection. So in some cases, like for this D, D only appears on this side. So we just replace it with the same thing over here. But A appears on both sides. So in some cases, so in the negative A, we take a disjunction, and in the positive A, we take a conjunction. This is to do with whether it's an entry literal or an exit literal. And it turns out that once we have this, it respects all the clauses, and these things are propositionally implied. Therefore, when we take quantifier witnesses, we just get this thing here, right? Because these are just going to be the witnesses, and they become single variables under quantification. Okay, so in that way, G simulates this QRAT. It's a bit complicated. Now, I want to talk about something that's very recent. This is maybe this idea that we can do a lot of this sort of like powerful simulation of QRAT with something much more simpler than the sequence calculus. And so before we had this extension rule, and I discussed where do you put these new variables in the quantifier prefix. And we always had to put them to the right of the variables they depend on. My observation is that if you just change the extension rule slightly, you can actually put them wherever you want. And this is now the new extension rule, where we say we've got some new variable that equals some function like an and, but we say only when some universal assignment is true. Now, this on the face of it may seem weaker, right? Because you can only really n is now only has some meaning under this particular universal assignment. But the advantage is now that n does not have to depend on the variables of alpha. So before, we had to put n after a and b, but if alpha contains a and b, you can actually put n even before them right at the beginning. And technically, n is actually no longer going to need to fit into a QBF prefix. It's going to be something called a DQBF. So DQBF is where you spell out explicitly which variables are depending on other variables. So when you have a variable to the right of another variable, you say that it depends on it. In the DQBF, you don't have this linear ordering. So you have explicit things. And with this n, depending on what alpha you choose, you can actually fit this n into anywhere. And once you do so, this is actually the sort of secret to simulating a lot of these QBF proof systems that don't have strategy extraction. So for example, like QRAT, various kinds of expansion combined with Frege, and all these other dependency schemes. And you could do the simulation without having to go through this strategy extraction technique as well. Because while that was very good in theory, a lot of the stuff with strategy extraction got very complicated, right? And strategy extraction in some ways was ending up as a bottleneck to efficient simulations. So now using this this new extension rule, we can actually sort of jump over that strategy extraction. And it turns out when you simulate this sort of like what this extended universal reduction rule is, you're actually using the same scheme that you used in G for that simulation. You're now just representing everything with extension variables. So you use independent extension variables to replace A, C, and D with annotated versions. And here what you do is you say that if U is false, then A, U is equal to A, right? So it's very similar to what expansion is doing. And then once you add in those variables, the problem is that because you have this particular U guarding it, this U also is added via resolution. But you can actually just reduce all those U's very simply because you have no more blocking variables because of the dependency. And in order to simulate extended universal reduction, technically what you're not doing is a reduction step. You're kind of shifting the formula to a different set of variables and reproducing all the clauses, and then removing And then the special case is the clause that you change. Okay. So I think this might be one of the final slides, yes. And just a summary of this trade-off between solvers, between strategy extraction and not having strategy extraction. So we've got this question, should solvers have strategy extraction? Well, in some cases, you actually really want it. So if you're using a QBF solver to solve a game, or even a circuit synthesis example, well, in a game, you don't just want to know who wins, you want to know how to win most of the time. In the circuit synthesis, your strategy is used for constructing the circuit. But you run into obvious problems like the select formulas. The select formulas, these are these examples where you have U if and only if some QBF is false. Well, they're obviously false just by very simple observations about the law of non-contradiction, right? So you might run into traps like that if you just require strategy extraction. So it could become relevant for perhaps a future QBF competition where you might have more powerful solvers that can defeat formulas that have hard strategies, but they may not be so relevant to certain practical applications. And maybe a suggestion here is to have different tracks, maybe a strategy extraction track or perhaps not. So how does strategy extraction relate to various proof systems? Well, it seems that this Fourier reduction seems to be linked to this strategy extraction, whereas using expansion-based techniques, you can sometimes beat these strategy extraction things. But then only when the underlying proof system is very powerful. In the resolution setting, they're very similar. Okay, so what about when sort of like checking, but doing some sort of like certification? If we're looking at two different tracks, one with strategy extraction and one without, then with strategy extraction, we kind of already have some good results. We have extended Q resolution is optimal as long as you can do all the only problem could be from this propositional hardness. And it also means that QRAT, which already has a checker, is probably good enough because it can simulate all those various things. And there might be some other optimal proofs based on more restrictive strategy classes. So you might require your circuits to be bounded depth, for example, and then you can maybe find some other optimal proof systems. Without strategy extraction, it's a bit more of a mess. We have various proof systems, and it's still a bit unclear about which one simulates which others. We know that G simulates QRAT, but we don't really know things like the other way around. So in the future, what we'd like to do is incorporate ideas maybe from G or from this independent extension rule in order to get something like a QRAT like checking format, or maybe sort of generalized to these like PR or other forms of this redundancy-based proof systems. That's my final slide. Thank you very much for listening.
A slightly provocative question. So if QRAT is good enough for solvers that do things that correspond to strategy extraction, then why don't we have any proof logging QBF solvers? Are people just lazy?
Well, there's still an open question for some solvers whether they have strategy extraction.
Okay.
Yeah, especially so in QBF at the moment we have like two kinds of solvers. One of them is working very much with CNF, but others work with sort of a circuit-based input, and it's a bit less clear what's going on in that. And there's some open questions for some of these solvers as whether they really do have strategy extraction, particularly when we don't know how to log them. And that might be the reason.
Okay. Any other questions?
Is this future something you're looking into, like trying to incorporate these more advanced?
Well, this independent extension is very recent, so we're still looking at like what this can do, and maybe at some point we run into like a roadblock there and think about like, is this enough? In particular, we're interested in what happens on the true side, because these are used for refutations, but in actual proof logging, you're actually also, you need, in a QBF setting, it's not like SAT where you just have an assignment. You actually need a proof as well.
Isn't it symmetric? Like somehow?
It's symmetric, but if you insist on a CNF format, it's kind of a bit weird, right? Yeah. So it might be that like this is using like a DQBF, right? It's turning a QBF into a DQBF and then various steps to sort of process it into another DQBF. But a DQBF is not a symmetric format, right? Because you have either a Skolem form or an Herbrand form. So maybe the next step is for me to really understand these second order QBFs, which are meant to like generalize DQBFs into something more symmetric.
Okay.
And maybe that's the answer, but yeah. And at that point, maybe we think about generalizing it into QRAT. There is a dependency version of QRAT as well, which we also simulated, but I don't think that's used.
Okay, so thanks again, Leroy.